Hello, I'm Dave Cunningham, Chairman of the Fiber Optic Sensing Association. I'd like to welcome you to our March webinar from the Fiber Optic Sensing Association member company, Senstar, titled The Benefits of Fiber for Electrical Utility and Perimeter Security. Our presenter is Stewart Dewar. He's a product manager with Senstar and is focused on their perimeter intrusion detection systems and the integration of those systems. So, Stewart, welcome. I look forward and everybody else looks forward to hearing more about your presentation.
Well, fantastic. Thank you very much. So good morning, good afternoon, and I guess good evening would be appropriate for some of our listeners. Thank you very much for joining. Uh, as said, my name is Stewart Dewar, product manager with Senstar. Pleasure to be here presenting today. And to set the background for my presentation, I'm just going to review the scope of the fiber optic sensing world. That FOSA's mission is to educate industry, government, and the public on. And fiber optic sensing can be broken down into three main sensing capabilities. First of which is distributed acoustic sensing, the ability of an optical fiber to detect vibration of the medium to which it's attached or embedded. The second main technology is the sensing capability rather, is distributed temperature sensing, the ability of a fiber optic to detect either the absolute temperature or the rate of change of temperature of the medium to which it's either embedded or attached. And then finally, distributed strain sensing, the ability of the fiber to make an absolute measurement on the degree of elongation, compression of the fiber, which is extremely useful for certainly structural health monitoring applications, for instance. So these three main sensing capabilities allow for a vast scope of applications, as shown illustrated here, ranging from pipeline condition monitoring using both acoustic sensing, temperature sensing, and strain sensing, to power cable monitoring, using the temperature sensing capability, the absolute temperature sensing capability of the system to monitor the loading rating of the cables, and everything else that's shown on the diagram. Today, I'm going to focus on the use of the distributed acoustic sensing for this application range here, primarily security, how this relates to perimeter intrusion detection systems, that kind of security. And to, again, set the baseline of what we're talking about, I'll just go over the basic concepts of a distributed acoustic sensing system. So here we have, typically the system would consist of some form of, normally a centrally located processor / interrogator / controller, whatever you want to call it, transmitting laser light into a fiber. Normally a single mode fiber, doesn't necessarily have to be, but it's normally a single mode fiber. And this light is very pure, highly coherent laser light. A small amount of that light is always reflected back from every point along the fiber, even though this would be a low attenuation fiber, but there's still some degree of reflection. Mechanical disturbances of the fiber will change the amount of light reflected from the point that is experiencing the disturbance. That's because the light being returned is actually the sum of light from multiple scattering points in the fiber, and when you change the relative distance between them, the interference, whether constructive or negative, changes, and that's what changes the amount of light that's seen back at the centralized processor. So even from this relatively simple picture of what's going on, we can see some important aspects or point out some important aspects. The sensing element is fiber optic. There's no electrical or conductive elements necessary in the field, to do the sensing. This capability enables sensing fibers to be multiple tens of kilometers long. This is an area of continuous development, just how far you can go, 40 kilometers, 50 kilometers, 100 in some cases, but long, I guess, is the main point. No signal return is required from the end of the fiber. which is important because that means if the cable is cut, detection continues up to the point of the cut, which is helpful to enable a capability we'll talk about later. And the system is very sensitive. This distributed acoustic sensor system is very sensitive to the extent that you can detect, vibrations in the ground coming from footsteps, which is a high degree of sensitivity that many other sensors used for a perimeter intrusion detection system cannot do. So that's somewhat unique to fiber sensing. And it's very accurate. So the disturbances can be located to a few meters or less. So that obviously makes it useful for a perimeter intrusion detection system application. So once you've got that basic technology, here's the kind of overview. You have sensor cable deployed on your perimeter, either on a fence, on a wall, or buried. The processor / interrogator is activating that sensor cable, and the information goes somewhere, right? At some point, some process or human is informed that there's something happening on the perimeter, and where it is, and to some degree what it is. Like, if it's buried in particular, the classifications can classify the intrusion to be footsteps, manual digging, machine digging, vehicle presence, and even more. And if the fiber cable is on the fence, then you can classify to, well, is it someone climbing the fence or is it someone cutting the fence? So this information can be presented to the security staff. The world of, who wants perimeter security, it's vast and quite variable in terms of the scenarios, from multiple distributed valve stations, which are small locations, but multiple of them along a pipeline. LNG plants, actually both the manufacturing of the liquefied natural gas and then the regasification plants also. Industrial facilities, whether it's a GM plant, etc. Logistics centers, airports, correctional facilities, not to forget that, and borders. And here's where we're going to go, talking about the application in the electrical infrastructure environment. Within that environment of electrical infrastructure, what do we find there? We find generating stations, whether thermal, nuclear, more and more wind, and more solar-based generating stations as well. Obviously the towers, and then the transmission substations, which are very much a focal point for security, because these are the substations that are deemed to be the most critical ones, because they're the substations where the power arrives to a town or city, right? And they're deemed to be the critical things, and the criticality of them can vary depending on what exactly they're providing power to. If they're providing power to data centers, to hospitals, to critical government infrastructure, or something like a refinery, their criticality will be increased and they are more likely to get perimeter security. And these roughly number, like worldwide, probably in the many tens of thousands of these critical transmission substations. And then we have the distribution substations, which there's probably one per 50,000 or 100,000 people in the world. So there's number in the hundreds of thousands or maybe even millions worldwide. This is the world of electrical infrastructure and the nature of the facilities that require protection. So why do the owners of these facilities care? Like, what's the motivation to do any investment, to have anything in the nature of security? They care, and I love this first bullet because it sounds so hyperbolic, but it's actually true. The electricity providers, utility companies, they want to preserve the continuity of supply of a critical resource that underlines modern society. Modern society does not do well without electricity. We know that. So the maintaining that supply is critical. There's workplace safety aspects to perimeter security in the sense that if there's vandalism, if there's theft, it's possible that the environment that's left is unsafe. It's unsafe for the workers, unsafe for the public who might happen onto it. If someone has stolen copper that's used to ground the transformer, that can be a very dangerous environment. So that's another motivation to have physical security. Support conformance to government regulations. For instance, in North America, there's the North American Electrical Reliability Commission that has many standards. One of them involves physical security that says that you have to analyze your physical security and have a plan to provide adequate controls. It doesn't actually say what you need, but it says that you should plan it out and make sure you have adequate coverage. Direct losses to theft and vandalism, like the owners of these types of facilities don't like it when they have expensive copper cables stolen from their systems. Any system needs to complement operational workflow, so you can't just seal the thing up with an impenetrable dome. You have to have a system that allows normal access to the thing. And ideally something that's cost effective for the range of sites that we just mentioned, from smallish sites to bigger sites. So what attacks, what kind of attacks are there to our electrical utility infrastructures? The most common people will tell you is copper theft, and it's kind of an asymmetric thing where someone steals a few $100s worth of copper, but they've created tens of thousands of dollars worth of damage. But this happens, and it's to be avoided and protected against. Vandalism, that's kind of theft for fun, and then the scary worst case scenario is terrorism or hacktivism. Low probability, but this is the nightmare situation of a cascading failure going across the continent and all of North America going dark. So people are very concerned about protecting against that. Okay, so I did say we talked about the benefits of fiber optic perimeter sensors for electrical utilities infrastructure, and here we go. Benefit one. On the perimeter that is to be protected, you have no need for power or grounding on the perimeter. Now, this is always a good thing for any kind of perimeter detection application because it reduces costs. It's a particularly good thing for electrical substations. There is either always or almost always an electrical grounding grid that underlays the substation. That means that any kind of cable laying just becomes a little more complicated. It's a tightly controlled thing. There's approvals. You need drawings. You just don't bring out your ditch witch and put a trench, from one point to the next. So it just complicates things, especially since a perimeter application is normally a retrofit. Like we don't want to only sell to stations as they're built. We want to sell to existing stock of stations. So again, this ground grid is there. Not having to mess with it or potentially damage it is an advantage, and that's a plus for using fiber optics around the perimeter because you don't need any other communication cabling, power, ground, etc. EMI and Lightning Immune. So, anyone who's I think AM stations still exist. If you had your AM station, you go near a power line, you hear the interference coming from the power line. So if you imagine putting some kind of sensor system on the perimeter, on the fence or near the fence, the obvious question is what will the impact be of the transformers, the switchgear, the overhead wires on that sensor? Now, whether it actually creates a problem or not depends. How high is the voltage? What's the current levels? How much separation from the wires to the perimeter? What specific EMI suppression and mitigation features are built into the sensor in question? So there is that analysis, that those considerations. But with fiber, it just simplifies the whole thing. It's not an issue. those specifying the system, those designing it, approving it, etc. They don't have to worry about the potential of EMI problems on the fiber optic cable because it simply does not conduct electricity or are affected by it. So this is a great simplification and is another plus for using fiber optic sensing cables for perimeter security around electrical utility sites. So what else? This is going to sound a little similar, but it's a different threat. No possibility of induced unsafe voltages on the sensor cable. Any conductor that is near a high voltage power line will be affected by the power line. There'll be some voltage induced onto the wire, cable, whatever, from the current and voltage flowing in the power line. And this is why people don't try to stay clear of. That's why there is a right of way. There's a cleared area under a high voltage power line. You're not recommended to go there, and certainly you wouldn't want to do something like pitch your tent under this power line because of the potential impact. This is another situation where the actual magnitude and the degree of the induced voltage, it's another depends. It depends how far away you are from the line. Depends on the current and voltage levels on the line. If you're on a fence, whether that fence is well grounded or not impacts whether this is an issue. The possibility of the high voltage being induced on your sensor cable. But again, with fiber, it just eliminates the concern. It's just not going to happen. You don't have to worry about it. You don't have to worry about whether your fence is well grounded or not. You're just not going to get induced voltages, from the power wires onto a fiber optic cable, which is a good thing. Another advantage stemming from fiber optics is that it's considered to be intrinsically safe. At the low power levels used for DAS sensing, which are typically the effective power is like a few hundred microwatts, really, because it's normally a low power laser that's done in a pulse mode. There's no possibility of that fiber, even if it were to become cut and the light was put into the environment, from igniting gases or clouds of dust that might be in the facility. Now, this is obviously a long-standing advantage that's quite relevant to oil and gas, where you could have, you've got tanks, you've got a transportation medium for gas that could leak, could create the situation. Now we're seeing the possibility in the electric utility world where hydrogen is becoming very much discussed, and pilot plants are starting to be built for so-called green hydrogen, which means hydrogen that's created by renewable resources, like shown in this plant here, where you've got the solar panels around the hydrogen plant, makes hydrogen in the day, and then hydrogen is used at night, for electricity. That's the basic idea behind green hydrogen. So if you have hydrogen, obviously we know, instinctively, the hydrogen is very, very flammable, and there have been some well-known tragedies resulting from that circumstance. That something that cannot ignite that hydrogen, should there be a leak, is a good thing. And again, another plus for using fiber optic cables in that environment. Another plus for fiber optic cables is that sensitivity that we talked about before, that allows the cable to be useful in many different installation environments, particularly the fact that it could combine, fence and buried being the classical, most used cases. And we have the sensitivity with fiber optic to get effective detection when the cable is buried. And you can have these mixed scenarios, right? In many parts of the world, even in North America, sometimes there's not a fence or not an adequate fence. Sometimes it's a wall. So the effective way to get perimeter intrusion detection could be to bury the fiber optic cable over some or all of the sensor, off the site. So being able to mix and match, so to speak, is a good thing. And having the distance to cover a long area is also good. Possibility to have a cut immune configuration. And this goes back to one of the key characteristics that was pointed out earlier in the fact that the fiber optic sensing will always work up to the point of a cut, even if the cable gets cut. So let's talk through this. What is cut immunity? It means that the full perimeter coverage will remain after one cut of the sensor cable. And that cut the concern could be either a deliberate cut in an attempt to disable the system or an accidental cut truck backs into the fence. And there's a little asterisk on full coverage. Normally you lose a few meters of coverage right on each side of the cut, but over thousands of feet of perimeter or more, it's considered full. How do you get a cut immune configuration? You get a cut immune configuration by covering the perimeter with two redundant fibers. The fibers must circle the perimeter in different directions. So if you look at this diagram carefully, this is a dual channel controller. You don't have to have a dual channel controller. You can have two single channel controllers. One of these fibers is going counterclockwise in this diagram. And the other fibers, the launch direction of the laser is the other way. So this is the setup. Now, also, one other thing you need other than the physical elements is the software to be smart enough to know that under normal circumstances, you're going to see two responses from any intrusion, and the software has to be smart enough to know that it's not two threats, one over here, one over there. It's really the same, coming from the same point, because you get two responses. So what does that look like when the fiber cable is cut? It looks like this. Again, one fiber is going to continue to operate up to the point of the cut. So this part's going to be covered. The orange fiber is going around the other way. It continues to work up to the point of the cut. So you have full coverage of your perimeter because of this basic property of being able to work up to the point of the cut. And modern systems are smart enough to report the location of that cut. So people know where to go look, to either fix it or know where there's this potential threat coming from. Possible to use spare fibers for data communication. So for a critical asset, the full physical security solution, it's not just going to be one system. There's going to be cameras. There's could well be a public address, general alarm system. There probably going to be some auxiliary sensors, like maybe a microwaves at gates or some radar units covering an area or duplicating the coverage. So there are a lot of needs for communication. These devices need to communicate back to the local control room or equipment hut, right? So we're putting fiber optic cable conceptually either on the fence or buried near the fence. Extra fibers in that fiber optic cable can become part of the communication network that's required. So to elaborate a little bit about that, so again, only one fiber really, or two if you want to do the redundancy thing, are needed for sensing. So there's plenty of opportunity to have additional fibers in your cable. Even a modest size cable, like no bigger than your small finger, can have 72 fibers or even more. So there's no shortage of capability to put fibers into a cable and onto the perimeter. Just kind of a typical cross section there. So these additional fibers can be used as part of the communications function, either trunking Ethernet, to having a fiber optic backbone to local switches, or as part of a proprietary setup, where if Senstar, for instance, has a proprietary networking scheme for our wireless gate sensor controller, so we can use fibers in the fiber optic cable as the communication medium to that controller that might be thousands of feet or kilometers away from the control room. So that's how using the spare fibers can facilitate the installation of the overall system. Scalable for different sizes of perimeters. So many vendors in the space offer very long-range systems, 40 kilometers, even higher. And it's possible to provide perimeter protection for even, I'm going to stick with this claim, for even the largest electric utility site with one centrally located processor. And my only hesitation on the claim is the monstrous size of solar farms that are being put in place with like gigawatts of capacity. But I still think it's true that even the largest one of those, could be protected with a single centrally located fiber optic system because of the vast distances that it can be covered. But it is impressive what you can read about these new solar farms. So why is it good to have one single processor? Well, obviously, cost-wise is that advantageous, but you only need to put something in one place because in this desert environment, you're going to have one control room that's your environmentally protected location. So you don't want to have multiple of those because they're expensive. You've got one system database to maintain and one location to go for system adjustments. There's just one thing to worry about, which is an advantage. So harking back to just that last slide, we have this vast distance that we can cover. Very legitimate concern comes up in a lot of customers' minds, like, oh, a centralized processor, it's a single point of failure, that processor goes down, the whole perimeter security system based on that goes down. So that is a legitimate concern, and how to resolve that. Well, it's not real magic, but you can add a redundant processor. People will say, do you need extra cable? No, you don't really need an extra cable because, again, you have all those extra fibers that are probably in the cable to begin with. You can simply use additional fibers to have a second system operating either in hot standby or cold standby scenario that's ready to take over if your primary system fails. And again, you need a little bit of software smarts so that your management system isn't getting multiple alarms every time one thing happens. It has to manage this failover scheme, so it's getting one stream of alarms from a healthy processor, not two alarms from the two processors. So this is the way to deal with the single point of failure concern, is have the redundant processor in the control room. So those are the main benefits. There's others we could have gone into a little bit, but those are the main benefits of using fiber optic sensing for perimeter intrusion detection applications with particular relevance to electrical utility installation. So what are they again? No power grounding required on the perimeter. The system is EMI and Lightning Immune. No possibility of induced unsafe voltages on the sensor cable. Intrinsically safe for explosive atmospheres for your hydrogen, green hydrogen plants. Easy to mix fence and buried sensing on the same system because we have the sensitivity that can do the buried sensing. You can put a cut immune configuration into place. You can use spare fibers for data communication. Scalable for almost any size of site. And there's means to avoid a single cost of failure that, relatively cost effective. So that is my presentation. Thank you very much.
All right. Well, thank you, Stewart. If you can go back to that last slide, so your contact information is up there. We're going to go through a Q&A session now. So if you have a question, there's the question function that's in your sidebar of the webinar controls, and feel free to pop questions in there, and we'll get to as many as we can during this, and those we don't get to, we will give to Stewart to send you an individualized response. But I'll start with just overall, Stewart, in general, how does the cost compare between an optical sensing system for that perimeter, for a given perimeter, versus the other options that are out there, which would, I guess, would be copper-based systems, or even radars and those kind of things?
Yeah, good question. Today, the fiber optic systems typically will cost somewhat more. Comparing like to like a fiber, fence sensor to a non-fiber or fence sensor, for instance. But very often, users have choice, and the market is telling us that very often, uh, paying that extra, the premium for the fiber optic system is well worth it, to get the benefits that we've discussed today.
Okay, and it's a couple of different questions about the type of fiber cabling package that you can use, and whether or not the type of cable that you use affects the sensitivity of the system. So there were some questions around flame retardant cable, loose tube cable, those kind of things. So are there recommendations or different types of different impacts based on the type of cable that I put on the fence?
The fence sensing application is relatively uh, forgiving in terms of the cable type, because you have a lot of motion on the fence. So uh, almost anything will work. I mean, obviously, this single mode fiber in almost any kind of cable construction uh, will work on a fence. Um, Varied, somewhat the same, although you have to be careful with not having too heavy an armor, right? Or too many layers of armor. Like, if you got double armor, triple jacket, at some point you start losing sensitivity that can impact the sensitivity of the buried system. And for buried systems, again, it's highly recommended to have the gel filled in the loose tube scenario.
Okay, and then
Um,
you mentioned armor. Uh, if it is an armored cable, explain the difference, armored versus a non-armored cable, in some of the electrical scenarios that you mentioned. Uh, does adding a conductive element to a cable, does that change the game?
Good question. So not much. There would only be one scenario. If we look at these benefits that are discussed, does having armor in the cable mean that you need power or grounding? No. Is it AMI immune still? Yes, because the fiber used for the sensing is still EMI immune. The only scenario where the having the armor changes this benefit summary a little bit is that you could get these induced voltages on the armor of the sensor cable if it's an armored cable. So that everything else applies
Okay,
the same to an armored cable.
all right. One more cable related question so far, and that is if I'm burying a fiber around the perimeter for protection, is there a depth, a maximum depth, minimum depth for
Hmm.
underground
Yeah, yeah, good,
implementations?
good question. Again, it does not appear to be overly sensitive. The sensor response, to footsteps and vehicles, etc., does not appear to be, overly sensitive to the depth. So anything, from a depth that would be adequate for protection, which would be, a foot approximately, up to 2 feet or 2.5 feet, like in centimeters, would say from 30 to 70 centimeters is a good depth. So you have a lot of flexibility in that area.
All right, and a question around the size of the perimeter. and maybe how the cost of the system versus the size of the perimeter um, interact. Assuming, I think the question's getting to it. A larger perimeter would be more cost effective on like a per meter basis than a small perimeter. Is that a fair assessment?
Yeah, yeah, that is a fair assessment because they're with the fiber-based systems that we've been discussing. There's essentially, um, uh, you know, I'll say expensive, or there's a rack mount processor that's a lot of value associated with that, right? So the longer the site, the more you're amortizing the value of that processor over it. So people will say, well, what's the cutoff? And it depends on. There's no one number that's the cutoff because it depends on the value that people put on the benefits described here. Like we've seen people use fiber optic, the ranging systems for sites of 500 or 600 meters, right? Which are kind of smallish for this technology, but they put value on these benefits. Um,
Mhm.
but I guess the sweet spot is probably anything from 3,000 feet up to roughly.
Okay. All right. There's a question here about is it recommended or not to place the cable in a duct or microduct? I'm assuming in a buried situation here, but we can talk about on the fence too. And what are the impacts of that in your experience?
So on the fence, it would not be recommended because um, the cable needs to move, to sense the vibration, and anything that attenuates the movement um, that would normally result from an intrusion is not recommended. Will be detrimental to the system. In the buried, it's somewhat so we would again, different vendors will have different uh, recommendations, but from Senstar's perspective, for instance, we would say no, don't put it in a conduit on the fence at all. Just like use an armored, you're better off using an armored cable because the there's this direct mechanical coupling from the armor, that the cable's built in to the fibers. It's much better than having it lying in a conduit. And the conduit will also screw up the ranging aspect because vibrations will travel down the conduit, and you'll have
Oh, kind of spread out
false.
that acoustic
It'll
signal.
spread it, and you might, one spot where the conduit is loose, some meters away from the actual intrusion could vibrate more than where the actual intrusion is. So anyway, conduits on the fence are not a good idea. I think we can, at least in my understanding, and definitely I would say that to any customer. Buried, it's a little different because it's a bit more uniform. The cable normally lays flat in the conduit. We still would not recommend it, but it's for some of the same reasons. Whether it's the coupling from the environment through the conduit through the cable is just less predictable than environment to cable direct. So we would not recommend it, but it is more commonly done because it's just a standard practice to put a cable in a conduit. So sometimes it's hard to stop people from doing that.
Yeah, well, and I guess the conduit does protect the ability to replace the cable over time and those kind of things, and probably is what's driving some of that discussion, right?
Yeah, exactly. It's the normal telecommunication way to install a cable.
Okay. Um, and then one last question on the cable or on the interactions there. How do you attach this cable to the fence? Is there a preferred method or a certification of some type?
Oh, good question. Very, very simply, we simply use cable ties. That's all there is to it. Doesn't need to be, there's nothing fancy about it.
Okay. All right, and then let's move a little bit, just for a few minutes, to talking about how the system, the interrogator that's, sitting there in the room and senses a disturbance, at sector 4 in perimeter, right? It tells you where it is, says somebody's climbing the fence. Then what? What happens? How do you interact with other security systems or the security personnel to get them that information so that they can act on it?
Yeah, that's a good question, and it's a area of constant evolution and development because there are many uh, so-called management systems, whether it's called a security management system or a video management system or a control system, but there's probably hundreds of them used around the world. So how do we get our information to them? Um, in some cases, there are standardized ways. There are some systems that have um, there's a so-called OPC standard or BACnet. There are some standards that like that provide a way to interface. There are a lot of custom integrations done because there are many vendors that don't have such standards. So every either the sensor vendor or the system vendor does a custom integration. And then there's also the fallback of which sounds like incredibly primitive, but still used, of closing relays, right? Where, for every alarm zone, there's a relay that will be closed. There'll be an alarm panel on the other side that receives that alarm, that detects that relay closure. And then that's the communication path into the system, which it's like, it's like
Right.
we shake our heads sometimes that we have to use that, but it works, right? It's like universal. Some people like it because it's simple and it's easy to debug. Like, does a relay
Mhm.
click? You know?
Yep. Right. So, and then on that same alarm handling train of thought, what about false alarm rates and those kind of things? Is the solution prone to false alarms, and are there mitigation options that you have for those?
Yeah, so all systems are prone to some degree of nuisance alarms. The main mitigation um, for a fence system is having a reasonable quality fence. Doesn't have to be like brand shiny new, doesn't have to be perfect, just has to be reasonably quality. And what does that mean? It means that the fabric of the fence, if it's a chain link fence, for instance, is relatively tight, and that it's fully attached where it should be. It's not just hanging off. There's like attachments point missing at the top or at the bottom or at the support post. It just needs to be relatively taut and fully secured at all points. That's the biggest mitigation against nuisance alarms. In the buried environment, it's a little different. The biggest mitigation is to have some spacing to to uh, to extraneous sources of vibration. Roads, uh, rotating machinery. The more spacing you can have from those extraneous sources, the better off you'll be. Trees also. But the proof of the pudding is in the fact that the number of happy users, right? Because all systems experience some degree of nuisance alarms at some points in time. If a hurricane comes through, you're going to have nuisance alarms, right? Uh, that's all there is to it. But there's many happy customers using many such systems from many vendors around the world, and that's the proof of the pudding.
All right. So we've got a few more questions that have piled in, but I think they're fairly specific to the requester. So I think we're approaching 45 minutes. So I think we'll close it off there. And I want to thank Stewart for putting this presentation together. All of the presenters that present in our FOSA webinar series put a lot of time and effort into their presentations, and I want to appreciate and recognize Stewart for doing that. His contact information is on the slide there. If you have any additional follow-up questions, you may want to jot down his address so you have it. But also, this webinar is going to be posted on our YouTube site. It'll be up there fairly quickly, hopefully today. And if you want to share it with colleagues, feel free to share that link around, and you'll be able to share this great content that we have today. So again, thank you, Stewart. And that concludes today's webinar. Thank you.
Thank you, Dave. Thank you, Joy, and thank you for all the attendees. Have a nice day.